crystals. And so that's it. It's a very easy synthesis process. And then we'll characterize our compound using various spectroscopic techniques. And now I request Dr. Suman Deshwakar to show you the mechanism for this set reaction. So I am stopping my presentation.
Yeah, thank you, Devasita. Unfortunately, we forgot to start the video at the beginning recording.
Okay.
Now I started, but anyway, so we'll have the instruction and then whole
Yeah.
the experiment there, and we can discuss later also. Not an issue. Mm, for explaining the mechanistic part, as always, I will share a Jamboard. Creating Jamboard. Yes. Send. Is it visible, the Jamboard?
Yes, yes.
Okay, perfect. All right. Okay, so let us start. Mm, as Professor Halder already mentioned, that this reaction is basically a bit unique in terms of couple of features compared to the previous experiment. First of all, is it's no solvent basically used here, so it's a dry grinding reaction. Okay, so no solvent used. So only the starting material and pinch of water just to make a pasty thing. Yeah, so this is one point. Second is no traditional energy source is there, like heating, or sometimes we use light, or nowadays electricity also used to activate molecules. These are not there, but rather mechanical energy. Okay, so the whatever mechanical energy we are using in this process is giving the molecule the enough activation energy to reach the transition state of the reaction and ultimately forming the product. Okay, so this is another unique feature. And third is the mechanistic part is the single electron transfer. That is also new to you, I guess. That is here. So one substrate, the reactant will allow to react these things, and the substrate will release the electron, and the reactant will take the electron. Single electron transfer will happen in a minute. I will write that. This is also another unique feature. And the products also having a unique feature, already Professor Halder mentioned there. That's the chirality, right? The chirality of the molecule. So fortunately, yesterday itself we discussed on with you guys only the axial chirality, but with this particular binaphthol we haven't discussed. That we'll discuss on Monday. But at least you know the concept of axial chirality with allene we have discussed, and I concluded yesterday's class, probably remember, that is allene is not the only thing, only substrate where the axial chirality exists. There are several other examples. These biaryls or specifically these binaphthols are another example. So that part I will leave for now, because Monday we are going to discuss in more details. Okay, but just for your information, these molecules are axially chiral. These are the things. So mechanistically, what's happening here? So this is our starting material, as you know. Oops, it's not working. Yeah, here you go. Yeah, this is our starting material. Two fused benzene rings, naphthalene, and one wedge makes it naphthol, beta naphthol. As you know, this is the alpha position, this is the beta position. So it is beta naphthol. Now what we are adding here? We are adding ferric chloride, which is a iron 3 salt, right? So iron 3 iron will be around. When we mix it in a mortar pestle, so what will happen? This iron, which is in higher oxidation state, it's hungry for electrons, all right? and this oxygen, as you know, having couple of pair of electrons, so just give one electron. One of this is the iron will fetch one of the electron from here. So you can see the single electron transfer, wherever we have to show, probably in second year you have learned this, we have to show half arrow in that these curly arrows, half, not full. When it's a full arrow, then it's a two electron transfer. When it's a single one, then we show half electron transfer. Okay? So by this way, what will happen? That's what the fate of the substrate. Fate of the substrate is this oxygen will lose one electron, and once it lose one electron, it becomes radical cation. So H is there. So one of electron is gone. So we will write this radical cation. Other lone pair is remains as it is. So this is the fate. And what the fate of the iron? Obviously, iron gets one electron. So by doing this, so iron 3 will become iron 2. Okay, so like this. So once now we are interested with the substrate. So once this form this, oxygen becomes plus, right here. So once and you know that oxygen hydrogen bonds is already polarized because of the electronegativity difference. That's why it's having hydrogen bonding and so on and so forth. So oxygen is already polarized, oxygen hydrogen bond. And now once this oxygen becomes positive, so this bond becomes even more polarized, right? Because oxygen was really pulling the bond pair of electron with hydrogen. Now it becomes positive, so it's really now needy for electrons. What will happen? So it will really pull the bond pair towards it, and it will release the proton. So this is, but look at the arrow, it's a two electron process. That's why it's release the proton. So minus H plus. Once it's to give so it becomes, you know, so ideally when you take a proton, suppose from the starting material itself here, if you release the proton from here, what will happen? It will become a O minus, right? O minus ion. But because this oxygen already lost one electron, okay, so this minus will not come. So it will remain as neutral. It lost one electron and gained one electron from the bond pair, so it will be ultimately neutral. But because it's lost one electron, it will remain as O dot. Okay, O dot, and two pair of electrons will be there like this. O dot. Just calculate electrons. You will come to know why it's O dot. If you're having problem in understanding, we'll discuss later. But let us first finish the mechanism. So basically, it's O dot. I'm showing this additional pair of electrons for your better understanding. You can skip those as well. Okay, but ultimately, this is important. This O dot is there. And let us finish the other part of the molecule like this. And this is of course in resonance. This O dot is bit stabilized, because it can go in conjugation with the benzene ring, and one of the benzene resonating structure will be like this, where the dot will come here. It will make a double bond. One of the, there you can draw several. I'm not going into that because this is important for to show the reactivity for us. So this is the thing. After one of the resonating structure, can the dot will come here. Now think about it. So iron is there, the substrate will there. We are continuously grinding. So this single electron transfer. By the way, I forgot to write here. This is, although I have mentioned, this is single electron transfer set process. There are several of this intermediate will generate in the mixture, right? Okay, because just by the single electron transfer and proton release, okay, several of this intermediate will form. Now think about it. This once these two of these intermediates will come closer like this. Okay, two radicals. So what may happen? That can be a radical coupling like this. Two radical will front, and now you can see this carbon bond formation will happen. This will give rise to this kind of intermediate. I'm drawing it here because we are making a carbon bond. One of the structure we have to draw upside down. Let us first draw the normal one. This is one. This is the new bond which is formed. We have to draw it upside down like this. Okay. like this. This is the new bond. This is the new bond which is formed hmm, by radical coupling. Now only one thing left. As you know, it was one hydrogen was there, right? So here one hydrogen was there. This hydrogen is still there. We are skipping it, but now we need that to show the hydrogen here. We can show it like this side. Okay. Just simple re-aromatization. You can release, re-aromatize. Same here. You can go there and go there, and we get our product like this. Tick tick. OH. So I get a stick. It should be like this. Just a moment. This double bond. Yeah, that's good. Its position should be here. See, there you go. Now, this is our product with OH here. So just you can see just single electron transfer, proton release, and radical coupling, and just normal traditional re-aromatization like any electrophilic aromatic substitution. We can get the product. Okay. So this is one theory, but some people also suggested that so because generation of these intermediates, so once you generate, this is quite reactive. Okay, so it may not, and it may not wait. This intermediate may not wait for another intermediate to come closer and react. Okay, so it may happen that this intermediate can react with another unreacted beta naphthol. Okay. So this radical coupling is not absolutely necessary to form the carbon-carbon bond. Hmm. It can form with this unreacted beta naphthol as well. So I will show you in a minute that mechanism, that's possibility as well. I need this. I need more space, so I will just clear the frame here and then show you that possibility as well. So here I will start with directly that intermediate, that radical intermediate. Here, this is our radical intermediate. Okay. So as I mentioned, it can react with another unreacted beta naphthol as well. So what I mean here, this is unreacted beta naphthol. Obviously, amount of which is higher, right? Because this intermediate you are generating slowly by reaction, but it's already there from the beginning. So it's quite probability is higher in principle that it reacts with this guy here. Okay, with this guy from here, one electron can jump. The aromatic system is known that it can react with radicals like cations. It can react like electrophilic substitution with radical also. It can react. Okay? So with that possibility, so I'm drawing this lower ring here and the other ring upside down. It's like this. What will happen because this double bond use one of is electron. There was two electrons, right? One of is the electron is used now to make a bond with the radical. So one will remain here on this carbon. So one will remain here and OH here. This is the new carbon-carbon bond like this. This is double bond. This is the other ring here. Yeah, this is the intermediate. Okay. So now two possibilities simultaneously will happen. This ring is ready to be re-aromatized, no problem. It will form just this proton will basically transfer here. It's a tautomerization like previous cases. But in this ring, it's still not possible. It's really need another single electron transfer here. okay? Because this ring cannot get aromatization because this extra electron is there. Okay, so this here it happen the same thing, that Fe plus 3 will take one electron and become Fe plus 2. This is basically a single electron transfer process and form a cation there. This ring is ready, it becomes OH. This is ring is getting to be ready here. This becomes OH still. This is plus because this radical went to iron. Okay, so this becomes plus, positive, radical becomes positive. Sorry, the benzene ring is probably not that nice here, but hopefully you can understand the thing. Now it becomes the aromatization happen and giving the same product. I'm not drawing the structure anymore. This binol. Okay. And one last notable thing here. Yeah, that's Devasys sir mentioned, showed you the amount of reactant we have used and all these things we are going to be using in the experiment. There you will notice that amount of iron we have used there, the stoichiometry is the amount of iron, the stoichiometric ratio is much lesser compared to beta naphthol. Because why I'm telling, you see, to generate this molecule, no, this intermediate, we need one iron 3 that will be converted to iron 2. And in the previous case, the mechanism where I've shown you the radical coupling, so there we need two electrons, two this kind of intermediate, right? To generate that two in this intermediates, we need two irons. So for each, so in principle, following this mechanism, and here also we need one. So if you see, if according to this mechanism, for each molecule of beta naphthol, we need one iron. So the molar ratio ideally should be 1 to 1. But actually in this reaction, we have used much less, much less. Okay. So then how the reaction is going then? The yields are quite good here. Why? So in principle, if you use only 20% of iron, so after 20% reaction, the reaction should stop because there is no more iron 3 to do the single electron transfer. But actually, it was shown that the reaction really finishes quantitatively and you get a nice amount of product. Then what's happening then? So that's only possible if somehow we regenerate iron 3 from iron 2, then only it's possible. So iron 3 by single electron transfer from beta naphthol for going to iron 2, and we must regenerate that one backward reaction to regenerate iron 3 so that again it can do this single electron transfer. It was found that yes, indeed, this regeneration is happening by our aerial oxygen. This aerial oxygen is known to oxidize iron 2 to iron 3. Okay, this just by our aerial oxygen, this dioxygen O2. Hmm. Because we are not using any inert gas, no argon, no nitrogen, just open air. We are grinding, so plenty of oxygen is there. So during the process, iron 3 is converting to iron 2, and this oxygen is doing the job and reverting this one or regenerating this iron 2 to iron 3, and this iron 3 again going back and reacting with beta naphthol. So it's a perfect example of catalysis also. Okay, so that's why at the beginning we have told you that there are several new features that we learn here. So there is, I did not mention at the beginning, I wanted to mention it at the end, that this reaction is also having the feature of catalysis. Okay, so this is a iron catalysis, single electron transfer from iron 3 to 2, and again going back, coming back to iron 3. Okay, these are the things. And the stereochemistry part of this we'll discuss in more details on Monday. Yeah. Okay, so any question, query? Yeah, if not, then I'll stop this one here. And Rasita, you want to say something, or should I play the
Oh
video?
no, play the video if there is
Okay,
one.
okay, all right. So let us see the video now. Then I need to share it the screen probably again. Hmm, share screen. It's there in my someone ping. Oh, just a moment. Some of it, I think. Mathura, okay, Mathur. The radical can form in many places of the benzene ring. Why doesn't it couple randomly? Yeah, it's a very good question. Yeah, it can really form. Yeah, true. Let us go back to the Jamboard. Very relevant question. Thanks for asking this. You see here, as I mentioned, this initially the radical form on oxygen, right? And then it can really go to different places. Yeah, that's true. But mm, uh, and even it can go to this ring as well. This ring as well, it can go. This ring, if you just continue resonance, then you see you can place here, it can place here, here, and here also. So it was found that this position or this alpha position is most reactive. Hmm. And there are a couple of reasons for this. Is this, you can explain this by the simply by the aromatic energy of benzene and naphthalene. The aromatic energy of benzene is 36 kilocalorie per mole. Okay, and the aromatic energy of naphthalene is 61. It's not exactly double, it's bit less. Okay, and now whenever this reaction happens, any substitution reaction or coupling reaction with involving the pi system of aromatic system, so in this intermediate, that aromatic energy gets lost. Okay, so that's why the activation energy is there, right? So is losing some energy, stability is going up, and then ultimately again when comes down when it gets the aromaticity again, regain the aromaticity. Okay, now think about it. When the naphthalene system is reacting, okay, when the resonance, this electron is still there, this present in this ring, okay, then you see in all cases, all the intermediates, the left ring I have drawn is a perfect benzene. Okay. So that means the loss of aromatic energy during the reaction is only 61 minus 36. So whatever number will come, so 61 minus 36. But now if you want to involve the push the radical here and generate a radical here and try to react with this ring, then you lose that entire 61 kilocalorie per mole. Okay, so that's why that activation energy, if you try to react this one, it's a possibility is there, mathematically possibility is there. You can push the electron and react with different position of this ring as well, but you will lose this entire aromatic energy, 61 kilocalorie per mole. But if you limit the reactivity here, then you can keep at least 36 kilocalorie per mole intact. So that's why any reactivity from this ring is having lower activation energy. Okay, that's why it's always prefer to react with this one. Yeah, yeah. Mm. This is the major reason. Okay, any other question? It's not says grow. Yeah. Okay. Thank you. Then we'll go to the video again.
Good morning, students. Today we are going to synthesize one on this two naphthol.
It's audible, right, Devasita?
Yes, yes, it's
Okay.
all.
Okay. Okay. Perfect.
Starting from beta. So this is a single electron transfer reaction. Also, we can say this is a solid state reaction, and again, this is a mechanical reaction. So the activation energy we will provide in this reaction by just simple grinding, just mechanical reaction. So what we will do, we will take beta-naphthol in a mortar pestle, and we will add ferric chloride, and we will grind and mix them together very well. So these are the ingredients that we need, the chemicals, that is the 2-naphthol, beta-naphthol, ferric chloride, anhydrous, and we have this mortar. So now we are taking 2.88 of beta-naphthol, the mortar pestle. And with that, we are adding iron, 0.7 gram iron chloride, ferric chloride, anhydrous.
Now you see the amount of iron is much less. Although the molecular weight is quite close. It's a bit hydroscopic, that's why it's sticking.
We will add 2 drops of water with this, and then paste with the mortar. So we are mixing nicely the ferric chloride with beta-naphthol. And we will continue this mixing for 20 minutes, and you see already a nice brown color, yellowish brown color is appearing from the mixture, and it forms a paste. So we'll continue this mixing for 20 minutes, and then we'll keep it on the table for 2 hours, and we'll occasionally grind it. So after 2 hours with grinding now and then, so now we are going to pour this material, the reaction mixture, in 40 ml water in a beaker.
So it's almost like making
We
masala.
are transferring the reaction mixture in 40 ml water in a beaker. So now we will boil this for 15 minutes on hot plate. So we place the materials, the reaction mixture on hot plate, and we will boil this for 15 minutes. And after 15 minutes, we will allow the reaction mixture to cool down at room temperature. So after 15 minutes boiling, we have made the reaction mixture cool at room temperature, and you can see we got a nice white precipitate of the binol. And now we are going to filter the binol using the aspirator. So we have aspirator, we have set up the Bugner funnel, and we are filtering the reaction mixture, the white precipitate of binol. So see, this is the white precipitate of binol, and we'll wash it with hot water.
This but washing is required to remove the iron, right?
And we will analyze this solid. It's like scale, scale-like solid. We will analyze with different spectroscopic technique and in layer chromatography. Thank you.
Yeah, that's the experiment.
Okay, so any questions, students?
Okay, someone asked Shiv Kumar. So why did color change from yellow to white precipitate? Basically, it was had a complex with iron. Binol is a very popular ligand also. As Professor Haldar already mentioned, with this couple of OH there, it can form a chelate with the metal ions. So that's from there the color was coming. It was already making complex with iron, and some other byproducts was also maybe there. But while purification, when we by boiling and filtration, when we removed this iron and all other junks, then it becomes white. The actual color of the product is white. This is not as conjugated as our dyes, right? So most of the small organic molecules are white in color or colorless, unless it's have really long conjugation like the indigo we have seen, the methyl orange we have seen. It really dyes a long conjugation when it's absorbed visible light, then only it becomes colorful. Otherwise, it's either white or colorless.
Sir,
Hmm. Yes.
so if Fe3 plus is like regenerated, then why doesn't the binol form a radical again, and then it keeps on happening? Like,
Yeah, it's possible. Some amount can react, but normally, as I mentioned, the reactivity is quite high in that position, that next to oxygen. Okay. Because of the gain of aromaticity, maybe 1-2% can form a polymer chain of binols, but because we blocked already by reacting the center, the alpha position of naphthalene by reacting, so then the reactivity is now becomes quite restricted. But this single electron transfer may happen, but this is reversible, so it will go there and again goes back to iron like this. Yeah.
okay.
And also the thing is, once you form this binol, right? So then the potential also change actually. Yeah, because binal is more that is definitely more conjugated this oxygen lone pair. Now it has option to go to previously only to the naphthalene ring. Now it can go to the other ring also. So that's why the availability of oxygen lone pair is comparatively less. This binal oxygen lone pair comparatively less than the beta naphthol itself. So when the availability of the lone pair of oxygen becomes low, then the potential becomes high. Any single electron transfer, it's associated with the oxidation or reduction potential. So that's what's happening. The initial reaction, this beta naphthol is getting releasing one electron. That means it's getting oxidized, and iron is taking one electron. That's getting reduced. Okay, so this oxidation potential and reduction potential of the substrate also plays some role. Okay? So if you just make two things and say, yeah, hope for single electron transfer, it will not happen, right? It will really need some matching on oxidation and reduction potential. And this beta naphthol having the oxidation of beta naphthol normally it more difficult than yeah, binol is more difficult than beta naphthol. Yeah, so that's why that polymerization process becomes very slow or almost not possible.
And it is
Sir,
also, sorry,
Hmm.
so it is also two binol forms a complex with one iron. And that's why whenever a binol is formed, it is transforming to the iron complex. And that's why if you consider the amount of beta naphthol and iron, it is actually 4 is to 1. So 2.88 and zero point 0.7 something. So it is 4 is to 1. That is the ratio. So that the once the binol form, it will convert to that iron complex.
sir,
Actually, that yeah.
why is it not reacting via oxygen radical? Rather, it is losing the aromaticity of the second ring and then forming carbon radical and then reacting.
Yeah.
I mean, it
So
could have regained
uh,
its retain its aromaticity and then react via oxygen
yeah,
radical.
so the oxygen radical can couple with another oxygen radical and form a peroxo bond. But this peroxo bond is very unstable. Peroxo bond can very unstable. It can during the reaction condition it can cleave again. Peroxides, the hydrogen peroxide. You just check the bond energies. Oxygen bond energy is very low. Even if it's coupled, it will break again and then form again this O dot O dot. This carbon once carbon forms is very stable. Uh,
I
because
mean, CO oxygen
yeah,
can couple with the carbon
CO
also.
is yes, CO is one possibility. Mm, but I think there, I think how to explain that. Mm, Probably the position of the radical, this carbon-centered radical, probably it's a more populated. This carbon the radical, so the because if you see the resonance structures, probably the carbon centered radical is more populated compared to the oxygen centered radical. This is can be one explanation. Mm, with bond energy I don't think can really, because oxygen carbon bond energy is also quite high. Other one is it may, yeah, I
No,
think so, this is yeah.
there is a possibility of reaction through this oxygen free radical also. And if you go through the books, IL Fina, the reaction of para tertiary butyl phenol in presence of iron, there you will see that the phenol are once it's formed radical, they are reacting within that. So bond formation between two oxygen, even with the atmospheric oxygen. So that means in between two benzene ring, there are four oxygens. So that's how all possibilities are there. So it's may form. But for this particular reaction we are going, so as the maximum product is the binol, so we are getting the binol mostly. But
Hmm.
there is possibility of all these things.
No, actually, yeah. Although I have drawn the mechanism quite in a simpler way, it's in reality it's not that simple. this because iron is around, this oxygen is always in close proximity of iron. This O dot or even so this iron is kind of protecting that oxygen always from reacting. That's also one major reason. Okay. This iron is always, because oxygen is a electronegative thing, no, and iron is a metal. So this complex is already there sometimes. This iron is somehow protecting this oxygen or inhibiting this oxygen to react. So rather, it's that's why the ring always prefer to react from the carbon center. Yeah, the iron has
Okay, sir.
some role as well.
Okay, sir. Thank you, sir.
Yeah. So I had a question which I have mentioned, Ryan. Let me check. I missed it. Sorry. Instead of oxidizing in air, the Fe can also be activated by light, which can also generate the radical and initiate coupling. Is it viable mechanism? You see, with light you can activate, but light cannot be used. So you see what's happening here. So initially we are using iron as oxidant, right? So we are oxidizing the substrate by taking one electron. And iron is converting it to iron 2 now. Hmm. Now we need more iron. So if you use just stoichiometric amount of iron, one equivalent of beta naphthol, one equivalent of iron, then no problem. Then we have enough amount of iron there, oxidizing reagent there. But now we are using less amount of iron, and this ultimately we are putting this aerial oxygen is there, which is ultimately acting as the rest of the oxidant. Suppose I haven't checked exactly how long, how much we have used, probably 20% like this. There was 25% or something like this. And so the rest 70% electron oxidizing thing is responsibility is going to aerial oxygen. Okay, 75% oxygenation is doing by oxidation doing by iron, although not directly via iron, but I mean the oxygen, 75% oxidation is happening by this aerial oxygen, not directly via iron. Now, with a light, of course, there are, probably you have read something about photoredox also by activating metal complexes by light. Light can activate a catalyst, okay, but it cannot give or take electron. It can just activate something, the catalyst. Now, in the excited state, it can take electron or give electron. That is more facile. But light cannot be any oxidizing agent. Okay, light cannot be, and light can promote electron transfer. Okay, giving by exciting something. Okay, but as a whole, light cannot be any oxidizing reagent. So you need at least stoichiometric amount of oxidant here, either in form of iron or by other secondary oxidant. In this case, it's oxygen. All right. Yeah, that's the thing.
So, okay, if there is no more questions, so I will go back to that presentation and show the spectra. Uh, just a minute. Yes, so we have synthesized the binol, and now we'll characterize the binol with spectroscopic techniques. So this is the UV visible spectra of binol. So what you need to check that see. So why binol is colorless? So we have got the spectra up to 350. That means it is colorless in visible region, and so it is, or you can see a white color. But this is the transition in UV, whether it is from N to pi star or pi to pi star, that you have to write. And then this is the FTIR spectra. So in binol, we have a lot of C double bond C, C single bond O and OH. And so we got the spectra. So you have to characterize the spectra. And this is the NMR spectra of the binol. So it's already mentioned here, everything is explained. So just you have to write in your laboratory notebook or in your notebook and send us the data. So if you have any further question, we can discuss that. So yes, please.
So probably have heard that chemistry is like cooking. but don't leak the spoon. And this today's experiment is a perfect example. Just making spices like this. But this, this mechanical reactions are nowadays becoming very popular. Although we
Yeah.
have done is in a mortar pestle, there are sophisticated instruments. So in my group, there is one ball miller. It's called ball milling. So where you have normally stainless steel chamber, and metal balls are there, small metal balls. So you need to put the substrate there, and this machine will just shake this metal jar in a very high frequency, and these balls will hit this substrate with the wall of that jar, so that it's a lot of mechanical energy generates and it will react. Okay, so this sometimes gives a really unique reactivity by doing so without any solvent, dry mixture, and so that the concentration of the reactants becomes very high, isn't it? Because whenever you add a solvent, you are diluting the thing, right? So this collision between the reactive molecules are becoming less. But if you can really do it in without a solvent, just by in a solid mixture, it's a very high concentration, and its reactivity sometimes very high. It was found that there are several reactions where in solution only giving 10-15% yield, and by mechanically this dry reaction giving more than 90% yields. Okay, so this is
Yeah.
very facile. And
Yeah.
industrial point of view, it's very easy without, because in organic chemistry we generate so much solvent. This is a big headache. In our laboratories, every week we are generating drums and drums after waste solvents, and it's and disposing those is really high. And if we can really save solvents, it will be good in terms of economic aspect as well as ecologic aspect. Yeah, so aspects, because we don't know how to dispose this. We can't really throw this like this. We have to either burn it or whatever. And burning, or as you know already, we are increasing global warming and all these things, and generate some poisonous gas as well. So this has really has good future, especially in industrial application. This ball milling or dry grinding mechanical reactions. Yeah. So it's good that you have learned this. Yeah. This one.
So I have already shared these slides with you in WeLearn. So please submit your notebook before next class. And if you do not have more question, so let us stop here. Thank
Yeah.
you very much, and have a good lunch.
Yeah. Thank you. Bye bye, guys.